Imagine standing on a lonely desert plain at night. The ground rumbles, the air turns to thunder, and above you a steel skyscraper of fire slowly rises on a pillar of white-hot flame. That moment, when hundreds of tons of metal break free from Earth and begin to climb, is the closest thing our species has to magic. Today we're going to peel back the metal skin of those machines. We'll see what a spaceship really is, why it's so insanely hard to build one, and how close we actually are to Star Trek-style travel. From SpaceX's Starship to nuclear rockets, ion drives, and theoretical warp bubbles, we'll go from launch pad to interstellar space. Stay with me to the end, because the last sections are where we get into the really wild concepts. Engines that eat black hole physics for breakfast, and what they would mean for the future of humanity among the stars. Before we jump to warp drives and sci-fi dreams, we need to define something surprisingly slippery. What exactly counts as a spaceship? A rocket is the engine and fuel system that gets you moving. A spacecraft is the vehicle once you're in space. A spaceship in this video is the whole integrated system, the machine that can survive launch, operate in vacuum, keep humans alive, and ideally, take them somewhere interesting and bring them back. We'll walk through that journey in roughly the order a real mission experiences it. First, escaping Earth's gravity well. Then, living in the brutal emptiness of space. Next, changing orbits, visiting the Moon or Mars, maybe landing and coming home. Finally, we'll zoom out to the technologies that might one day let us go far beyond our own star. Think of this as a guided tour through the anatomy of a spaceship and the future of human migration into space. To build a spaceship, you first have to escape the biggest prison ever constructed, Earth's gravity well. The key number to understand is orbital velocity, about 7.8 kilometers per second for low Earth orbit. That's roughly 28,000 kilometers per hour sideways. A spaceship doesn't really go up into space. It goes fast enough that as it falls, Earth curves away beneath it. Getting to that sideways speed is brutally hard. Chemical rockets work by throwing mass backward at extreme speed. Newton's third law does the rest. But rockets are horribly inefficient. A typical orbital launch vehicle is mostly fuel, the elegant crew capsule or sleek upper stage on top. That's the tip of a skyscraper-sized flying fuel tank. Engineers fight this with staging, dropping empty tanks and engines along the way. Reusability, like SpaceX's Falcon 9 or Starship booster, attacks the other problem, cost, by landing those stages instead of throwing them away after a single launch. Chemical rockets are our workhorse engines, but they're barely good enough to reach orbit and terrible for going much farther. So what else can we use to power a spaceship? At the basic level, a rocket's performance is defined by specific impulse, a measure of how efficiently it turns propellant into thrust. Hydrogen-oxygen engines are great, but to really explore the solar system, we need better. Nuclear thermal rockets use a reactor to superheat hydrogen, giving roughly double the efficiency of chemical engines. Projects like NASA and DARPA's Draco aim to test this in space in the 2030s. Electric propulsion goes further. Ion engines and Hall effect thrusters gently push ions out the back, producing whisper-soft thrust for months or years. The result? Enormous total velocity change and incredibly efficient deep space cruising, perfect for robotic probes and potentially for cargo ships. Each propulsion system reshapes what a spaceship can realistically do and how far it can roam. Once you've fought your way into orbit, the rules change completely. Aerodynamic forces vanish. There's no up or down, only velocity and gravity. Spaceships in orbit live inside a constantly falling frame of reference. To change where you are, you don't steer like an airplane. You perform carefully timed burns. A short engine firing at the right moment can raise or lower your orbit, shift your plane, or set you on course for the moon. This is the domain of orbital mechanics, sometimes called the celestial clockwork. Home on transfer orbits, gravity assists, and free return trajectories are the tricks mission designers use to stretch limited fuel into ambitious missions. Modern spaceships rely on precise navigation, star trackers that read constellations, gyroscopes that sense rotation, GPS when near Earth, and deep space radio ranging when far away. The cockpit may look sleek, but beneath it is brutal math determining whether your spacecraft kisses a planet or misses it by millions of kilometers. A true spaceship isn't just a flying robot, it's a tiny closed world that has to keep humans alive in an environment that wants to kill them instantly. Inside the pressure hull, engineers have to recreate the essentials of Earth: air at the right pressure, oxygen levels that won't suffocate or ignite everything, carbon dioxide removal, temperature control, humidity, and protection from deadly radiation. Modern crew vehicles, like SpaceX's Crew Dragon or NASA's Orion, use a mix of consumables and partial recycling. The International Space Station goes much further, recovering most water from humidity and even urine, and scrubbing the air with complex chemical systems. All of this runs through layers of redundancy and fault tolerance. A leaking valve or failing pump in space isn't just an engineering issue, it's a life or death emergency. Designing a spaceship interior means balancing safety, mass, and human psychology, windows for sanity, shielding for survival, and systems that can be repaired by a tired astronaut with limited tools. Every spaceship is a wrestling match between mass and capability. Every kilogram you launch demands more fuel, more structure, more cost. That's why spacecraft interiors often look surprisingly cramped and utilitarian compared to sci-fi sets. Engineers obsess over the mass budget. Thicker radiation shielding, that might mean less water or fewer instruments. Larger fuel tanks for a Mars trip, then you need a bigger launch vehicle, which cascades into more complexity and money. Modularity is one way out. Instead of a single monolithic starship, you can assemble a mission from specialized pieces: a transfer stage, a lander, a habitat, a re-entry capsule. The Apollo program did this. Future Mars missions probably will too. Companies like SpaceX are betting on another strategy: giant, fully reusable vehicles like Starship, where economies of scale and mass production make big payloads affordable. If that works, the mass trade-offs change, and spaceships can afford to be more capable, spacious, and comfortable. For most of space history, our spaceships have stayed near Earth. That's beginning to change. Let's look at a few real vehicles that define the state of the art. NASA's Orion capsule is built for deep space missions, high-speed re-entries from the moon and beyond. It rides atop the Space Launch System, a massive expendable rocket. SpaceX's Crew Dragon handles routine crew rotation to the ISS, sitting on a reusable Falcon 9. It's relatively minimalist, almost like a space taxi. Starship, if it achieves its goals, combines them: enormous payload capacity, full reusability, and the ability to go to the moon and Mars in a single integrated system. Its stainless steel body, heat shield tiles, and belly flop landing are all radical design choices. Meanwhile, China, Europe, India, and others are developing their own next-generation crewed vehicles. The geopolitical and commercial race is creating a diverse ecosystem of spaceships, each optimized for slightly different missions, budgets, and philosophies of exploration. So what about going back to the moon and staying there? Lunar missions push spaceships into a harsher, more independent role. A lunar ship has to handle longer transit times, deep space radiation, and high-energy re-entries. It also has to operate far beyond the safety net of quick rescue. Artemis missions will likely use a combination: SLS and Orion to carry crew, a lunar orbiting platform called Gateway, and a dedicated lander, potentially based on SpaceX Starship, to reach the surface. On the moon, dust is a nightmare. Razor-sharp regolith can shred seals, joints, and radiators. Spaceships operating there need robust airlocks, dust-tolerant mechanisms, and careful landing plume management to avoid sandblasting nearby hardware. Long-term, lunar ships may evolve into ferry vehicles that shuttle between lunar bases and orbit, never returning to Earth. In that model, Earth-launched spaceships become just one link in a permanent cislunar transportation network. Mars changes the game. It's far, it's cold, and its thin atmosphere is just thick enough to cause problems, but too thin to land heavy things easily. A Mars-capable spaceship needs serious life support endurance, months in transit each way. It must also handle long communication delays, so onboard autonomy and crew self-reliance become critical. Entry, descent, and landing at Mars is notoriously tricky. Parachutes help, but supersonic retropropulsion, firing engines directly into the thin air, is likely necessary for large ships. Starship's design is heavily influenced by this challenge. Then there's the return trip. Unless you're planning a one-way colony, your spaceship needs either enough fuel to come back or a way to make fuel on Mars. In situ resource utilization, turning Martian CO2 and water into methane and oxygen, is a cornerstone of most serious Mars architectures. If we crack that, Mars ships become more like refuelable airliners than disposable expeditions. So far, our spaceships are confined to the solar system. Crossing to another star with today's technology would take tens of thousands of years, but engineers and physicists have sketched more ambitious concepts. Project Daedalus and later Project Icarus envisioned enormous fusion-powered starships, burning pellets of deuterium and helium-3 to accelerate to perhaps 10–20% of light speed. These would be unmanned probes, still requiring multiple human lifetimes to reach nearby stars. Antimatter drives promise even higher performance on paper, but producing and storing antimatter in useful quantities is far beyond our capabilities. More realistic, at least conceptually, are beamed propulsion ideas. A lightweight sail pushed by powerful ground-based lasers could accelerate a tiny probe to a significant fraction of light speed. Breakthrough Starshot is actively exploring this, aiming at gram-scale spacecraft. These aren't ships you can step inside yet, but they map the extreme edges of what a spaceship might eventually become. Then we reach the ideas that blur the line between engineering and pure speculation, warp drives and wormholes. Einstein's relativity doesn't let you accelerate a spaceship past light speed, but it doesn't strictly forbid bending space-time itself. Theoretical models like the Alcubierre warp bubble describe a way to contract space in front of a ship and expand it behind, effectively surfing a wave of distorted space-time. The catch: early calculations required more energy than the observable universe and exotic negative energy matter we've never seen. Newer refinements reduce the energy budget dramatically but still leave us in the realm of far future physics. Wormholes, shortcuts through space-time, pose similar challenges. Even if they exist, stabilizing one big enough for a spaceship looks extraordinarily difficult. These concepts matter less as near-term engineering and more as boundary markers, showing us where the real laws of the universe might allow, or absolutely forbid, future starfaring civilizations to travel. Building better spaceships isn't just about hardware, it's about who gets to use them. For decades, only superpowers could afford rockets. Now, falling launch costs and commercial innovation are opening space to startups, universities, even individual creators. Private space stations, in-orbit manufacturing, asteroid mining prospects, and point-to-point Earth travel on suborbital hops all depend on cheap, reliable spaceships. Reusability, standardized docking ports, refueling depots, and on-orbit servicing could make spacecraft more like today's global aviation network. But there are risks. Crowded orbits increase debris and collision danger. Military applications blur with civilian ones. Resource claims on the moon or asteroids raise thorny legal and ethical questions. The spaceships we choose to build, gigantic national flagships, nimble commercial taxis, or autonomous robotic fleets, will shape the political and economic future of space. We're not just designing vehicles, we're designing the architecture of a multiplanetary civilization. Let's zoom out and connect the dots. To get off Earth, a spaceship must hurl itself sideways at orbital velocity using brutally powerful rockets, chemical, nuclear, or electric. Once in space, it trades wings for equations, navigating by gravity and carefully timed burns. Inside, it's a fragile bubble of Earth, keeping humans alive with complex life support systems, shielding, and careful mass budgeting. Different missions, lunar sorties, Mars expeditions, deep space probes, drive radically different designs, from compact capsules to sprawling modular ships. On the horizon, fusion drives, beamed sails, and other advanced propulsion concepts hint at interstellar travel, while warp drives and wormholes sketch the distant edges of what physics might someday allow. And wrapped around all of this is a shifting human story: governments, companies, and communities deciding what to build and why. Spaceships are not just machines. They're the tools we'll use to redraw the map of where human life can exist. The revolution has started. It's just unevenly distributed. If you've watched this far, you're exactly the kind of person who should stay plugged into where spaceships are heading next. On this channel, we dive deep into the engineering, physics, and big picture implications of space technology, always with an eye on what it means for ordinary people in the coming decades. So here's what you can do right now. Hit subscribe and turn on notifications so you don't miss upcoming episodes on Mars mission architectures, nuclear rockets, and realistic Starship designs. Drop a comment with the spaceship concept that fascinates you most, or the one you're most skeptical about, and why. Share this video with a friend who still thinks rockets are just big fireworks. The more people understand how spaceships really work, the more pressure there is to build them responsibly and ambitiously, because one way or another, some generation will become truly spacefaring. The only real question is whether we're early spectators or active participants.